Morning, everyone. And yeah, today is the last. I mean, we officially we have one more day, but this is the last day with invited oral sessions. And it's glad to see that we have three very renowned professors in this field. The first talk will be given by Professor Ozawa from Tomoki University. So please welcome the speaker. Good morning, everyone. So I'm Tomoki. I'm a theoretical physicist from Tohoku, Japan, and this is the title of my talk. And I first obviously want to thank the organizers for inviting me here. I'm very happy to be here. It's a pity that I could only attend the last couple of days of this 2-week conference, but I'm still having a lot of interesting discussions and also looking forward to seeing more interesting things this afternoon. So this is actually my second time to visit Daejeon. The first time was in 2019 after the conference, and I attended the conference here, and I also had a very nice time there. And I feel like I should mention that. So this is the website of PCS that I took a screenshot this morning, and yes, so this is me. So this picture I think was taken from the conference in 2019. I'm very glad that this photo. It's always been on the website of the CP. I feel like I'm a part of this ideas. Yes, and yes, so here's the outline of my talk. So today my talk is about quantum metric. And I heard that there are many talks about quantum metric last last week. So I don't know if I need to introduce quantum metric now, but still, this is what I should do today. So yes, I start from the definition of the quantum metric, and then I explain some of the physical implications or physical significance of quantum metric. So one is on localization, and the second is an optical response. And I also mentioned some of the recent measurements of the quantum metric, especially those that I'm involved in. And so here's the outline, and let me start from the definition. Okay. A lot of things written here. So my talk today is about a geometrical property of quantum states. And here's the setup. So I have some quantum state psi, which depends on the set of parameters, which I call lambda, or the bulk of lambda, which and there is several parameters that quantum states can depend on the one. And these parameters can be anything. So it can be some externally controllable parameters, or in many cases, it's quasi-momentum in a lattice setup, or anything. So let me start from something very general. So typical situation that this happens is when the Hamiltonian depends on this set of properties. And then Hamiltonian has a set of eigenstates and eigenvalues. So for example, we can obtain the eigenstate and eigenvalue by solving the eigenvalue equation. And this eigenstate, which has some bound index n, which can depend on set of parameters lambda. So this can serve as this quantum state, which depends on this set of parameters. And yes, please.
What about the other? What about systems where you don't have state translation? Right?
Sorry, what you speak louder?
You don't have translation variance.
Okay, thank you. So here I'm not I'm not assuming any translation invariance. So this is just Hamiltonian, which depends on some parameter.
So you just have a parameter. But if I have the other system,
Yes, you can. Yes, you can. But yes, you can. But in that case, I think you need to consider some fixed disorder to define quantum states. And I don't know the strength of the disorder is the right parameter here. Crystal. The quantum crystal in the setup you consider have some parameter dependence. For example, I think the quantum crystal. For example, disorder system, what you can do is you can consider periodic boundary condition, and then you consider like a twist phase as a periodic boundary, and that can serve as a parameter.
Can you see
Yeah, that can be for any system that's in transitions. Thank you. Thank you very much.
Don't worry.
Yes, and so I consider my talk the situation where this Hamiltonian is n by n permission matrix. So I consider a finite size Hilbert space. I don't consider an infinite dimension Hilbert space. Everything can be also done in infinite dimension Hilbert space, but doing positive finite size is easier. So let me assume infinite size Hilbert space. Yes.
Does it need to be Hermitian? Can it be applicable to non-Hermitian system?
It can be applied to non-Hermitian systems as well, yes. But then some of the property that I explained and physical implication should be considered. But you can also consider non-Hermitian stuff as well. Yes.
I can relate. You think about the also normal I basis state. We can define the matrix. Not the non-orthogonal matrix.
Non-orthogonal
basis state.
You're talking about the non-Hermitian system?
No, that depends on the non-Hermitian. Selection of the basis.
So here I'm not. So here I just have a set of quantum states and just one state. There's no like a set of bases. It's just one state so far.
But my point is a different point of view. You think about the wave function. There are the basis wave function, but the basis wave function is a non-Hermitian. We can define the metric, kind of metric.
Right, guys, can I interrupt? Sorry, guys. We just see one slide, some definitions. There's nothing to discuss yet about. And let him continue and ask later, because otherwise we'll never get to the interesting stuff. Okay, sorry for that, but let's just continue.
Okay, we'll discuss later.
Wait 5 minutes.
Okay, so my quantum state is like a vector. Element and Hilbert space is a vector. So in this parameter space, depending on where you are, so this vector can direct in different directions. And the geometrical property of quantum states tells you how these vectors, the quantum state, change in the parameter space. So like if you want to go from here to here, this arrow tilts a bit. And the geometrical property tells you how much this tilt is for the given point in the parameter space. Yes, and yes.
Sorry, so the vector that you created is the vector for all the eigen states or just one state and all the parameters?
Just one. So people often distinguish between geometrical and topological properties. And let me briefly explain what this is. So the geometrical property tells you how much the quantum states change locally in the parameter space for a given point in the parameter space, how much these arrows tilt. And some examples of the geometrical properties are very phase, very curvature, quantum metric, and so on. And so quantum metric is a geometrical property in this sense. But there's also another concept of topological property, which tells you how much this quantum state changes globally in the parameter space. So if you look at the entire parameter space and how much these arrows change. And some examples of topological properties are Chern number, winding number, GT topological invariant, and so on. And so here's a schematic picture of the difference between these. So consider one-dimensional parameter space, and these arrows, rotate. And so topology tells you that. So topological properties of these arrows, if you go from the left hand to the right hand, these arrows rotate once. So rotating once is the topological property of these quantum states with arrows. And the geometrical property is locally how much these arrows tilt. So this local change is the geometrical property. And typically geometry and topology are closely related. So in this case, if you integrate the change of the direction over the entire space, you get like 2 pi, which tells you that the arrows are rotating once. So usually they are closely connected. But today my talk is about the the quantum metric. Okay, so I'm gradually going to define quantum metric. So quantum states, so let's look at this quantum state, so psi of lambda, as a map from some parameter space to the space of quantum states. So the space of quantum states, it's a n-dimensional complex vector. But wave function multiplied by some overall constant is still the same state according to quantum mechanics. So what we need to consider is to identify different complex vectors which differ by an overall factor at the same state. That will mathematically give you the space called the complex projective space. So don't get scared if you haven't heard of this name. It's just a name for the space by identifying different vectors which differ by overall constant, same thing. Okay, so the quantum metric, which is a topic of this talk, is a metric defined on this side of on this space, on the parameter space. And so I want to introduce the metric. So a metric is how to define the lengths in your parameter space. So how to define the distance between different points in the parameter space. And so I want to define distance here by looking at where the 2 points map on this side, and if these 2 points here on this side are close or far on this side. And on this side, there is a well-studied, well-known metric, which is called the Tomoki study metric, which is to tell you that if the two states, the infinitesimally close 2 points, so if you consider 2 points here, and if the inner product is close to 1, that means these two states are very, very similar, then the 2 points here are close. So if this inner product is close to 1, then the distance is close to 0, so they're close. But if the 2 points, the inner product is far from 1, then the two states are very different. That means this distance is larger. So that's how you define the distance here, from here. And so mathematically speaking, what I want to do is to define a distance here through the pullback of the distance defined here. So what I mean by that is I define a metric here, which I call Gij on this side, by using this distance on the right side, but by looking at the 2 point lambda and close by point lambda, so 3 lambda, and looking at the distance of these 2 points on the right side. So this is how I define the quantum metric. Yes. Yes.
Why Tomoki study metric? Why not some other metric, say Fisher metric or like other trace preserving, other trace distance measures?
I don't know. I mean, this is a distance that you can define from the inner product of the quantum state, and that's a very natural thing to consider in physics. But I think if you want to use other metric, then you need to consider some more perhaps artificial thing on the right-hand side. But here it's made of really the constructed out of the quantum states.
What do you have in mind?
Like a Fisher-Rao metric kind of thing.
This is real, not complex. Real version of Tomoki study is a tissue.
Okay.
Okay, so yes.
Now, it's a related question.
Yeah.
But do we expect to change the metric? And I think it's just like what we metric, any sensible metric.
Physically, so it depends if the metric that you define will have some physical significance or not. For example, okay, so Berry curvature can also be defined in this way. So there's a curvature or the symplectic structure here, which we'll pull back here, and you get the Berry curvature here. But there are also many like infinite parameters of curvature that you can define here. But then why do we consider Berry curvature? Because that's a very natural curvature that you define from the inner product of the quantum state structure, and that also have very many physical appearance in physical structures. So yeah, I would say this is the reason I consider this is it's naturally made out of the inner product structure of the quantum states, and also it has physical meaning. That's the main reason. But you can also consider other metric, and if that appears in some interesting critical setting, that will be also good. I mean, but that's also totally fine.
Question is this dimension of the parameter space lambda assumed to be always much smaller than capital N, or can it be anything, or
So capital N should be 2 or higher, and can be anything, and it doesn't depend on the dimension of the parameter. So the parameter space here can be any dimension. It can be 1, 2, 3, and it doesn't depend on the size here.
so there's no issue with defining this metric in the lambda space, no matter how high dimensional this lambda space
That's
is.
right, that's right. There's no issue. No.
And just a rhetorical question. I mean, this is essentially linear algebra.
Yes.
So was this stuff studied maybe before even quantum mechanics was known to humans? Was it? Is there something which is called not quantum metric but somehow different? If I open a linear algebra book, so I can find these kind of mappings also there.
So it's called Rubin study metric. So, and also in the early days of the quantum metric study, people call it Rubin study metric.
Okay.
Because it's essentially Rubin study metric seen in other spaces. Okay. So now I try to write the quantum metric in a more friendly or less. I don't know if it's friendly, but in a concise way. So this is the quantum metric. So this is how I define it in this talk, the quantum metric. Okay, but so to get the concrete form of the Gij quantity metric, so what I do is that I expand this quantum state in Taylor series in terms of this d lambda. So I just do the series expansion. The first term here, so the first order term, second order term, and the higher order term.
But you're using the Taylor expansion. Normalization condition is sometimes broken, right? Due to the error. Normalized condition, original
Here, this is a higher.
Normalization.
normalization condition, original wave function.
So normalization of psi.
Both is in my memory, sublimit the Tomoki study metric has some denominator.
Yes.
to normalize.
So I'm assuming here that this psi is normalized.
But both are normalized.
What is both?
Both of them.
Psi lambda plus d lambda state is also normalized.
Yes. That's true. Yes. Thank you. Sorry, yeah. I'm assuming normalized. Thank you. So I expand, and the zeroth order term cancel. 1 is 0, and you can also show that the first order term also vanish. So you can also show that the first order term is 0. So the lowest order term is the second order term, the lambda, the lambda j. Okay, so you can write it in this way, the second term. So there's some first term, and then the second term is obtained by interchanging ing. So you do the symmetric sum on this indices. And so, and extracting the coefficient here, the quantum metric is of this form. So there's some first term and the second term where the I and j interchange. Okay, looks complicated enough to me, but let me explain what this is. Okay, so it contains the derivative of states in lambda I and lambda j direction. So it tells you how this quantum state change in two directions. But inside there's this factor 1 minus projector to the state. And I'll show in I think next slide. But this projector has a very important role to make this quantity gauge independent in a sense. We change the phase of psi. So I'm assuming to use a normalized wave function, but we still have a phase degrees of freedom. But because of this projector here, this entire quantity here is phase or gauge independent. So it can have some physical. So this is the definition of the quantum metric, or sorry, this is the complete expression of the quantum metric. And alternatively, many people also introduced this quantity called a quantum geometric tensor, which looks very similar to what I showed you. Yes, please.
Sorry, I probably just missed it. So the higher order terms just go away.
the quantum metric is defined as a coefficient of the second order. So this is a quantity called the quantum geometric tensor. And it looks very similar to what I have here. So the difference is that here I'm taking a symmetrized sum between I and j, so the direction when you take the derivative. Here I'm not symmetrizing it. But other than that, there's this projected other state and a very single structure. So this quantum geometric tensor is also gauge independent. So you change the phase of this quantum state, you can show that this quantity, the quantum geometric tensor, doesn't change. So you can have a physical meaning. And it quantifies how these quantum states change if you move in I or j direction. And the quantum geometric tensor has a nice property that its real part is a quantum metric. So you take this quantum metric and you take the real part of the quantum metric. That's given by, okay, so the quantum metric, quantum geometric tensor plus its complex conjugate. Complex conjugate is obtained by changing I and j here. That's exactly the expression for the quantum metric that I showed in the previous slide. So the real part of the quantum geometric tensor is the quantum metric. But the quantum geometric tensor also has an imaginary part. So if you take the imaginary part, you can show that this quantity is what people call very curvature. So the real part of the quantum geometric tensor is the quantum metric. Imaginary part is a very curvature. And so by looking at the quantum geometric tensor, you can discuss both of these geometrical properties using one, let's say using one concept. Okay. And yes, please.
A nice question.
Yeah.
In the previous slide, this psi that you have taken, it is still the one eigenstate that we considered, right?
That's correct, yes.
Okay. So if I have listed like a superposition of eigenstates, say all the superposition of eigenstates, then this projector will go zero, right?
Okay, so I am not assuming that this psi is an eigenstate of anything. I mean, that's often the case, but generally this psi can be any state which depends on the parameter. So it can be a superposition of state, that's also fine. Here, there's nothing about the eigenstates.
Okay.
But you started with an eigenstate. Your story started with an eigenstate. And now you say you can take any state and just assume that you have some lambda dependence which moves your state around the Hilbert space, right?
No, I didn't start actually. It was a confusing point.
Okay.
But, so I said typical situation is when you have an eigenstate. Right. That's just a typical situation. But generally, you can take anything. So it doesn't need to be eigenstate.
And if I take an eigenstate,
Yes.
then it has some dependence on lambda, whatever it is, and I get a metric. Now let's say I take any vector and I tell this vector you have any dependence, but on some lambdas in the same lambda space with the same dimension, but anything. Will I get the same metric or will I get something different? I will get something different. Right?
Different, yes, that's right.
Smoothness is important. I mean, wave function should be a smooth. I mean, regarding with lambda.
Yes, wave function should be smooth. Yes.
So this is related to Sergey's earlier question. If, I mean, can you always define a pullback? The dimension of lambda, certain dimension of lambda, if you have, then maybe you cannot define the inverse and then you cannot define a pullback. Can this kind of situation arise?
So you're right. Okay, so if I just write quantum metric in this way, you can always calculate it, and it's fine. But it's true that I say quantum metric is a metric, but there can be some points in the parameter space where the quantum metric is not a good metric anymore. So there can be some singular points, and particular where there can be some singular points where the determinant of the metric becomes zero. So the metric should be positive, definitely quantity, but there can be some points where the metric becomes, say, zero, so singular. That's possible.
But what I'm saying is that if the dimensions don't match, if I don't know which way it goes, maybe the dimension of lambda is much higher than n. In that case, is the pull vector still defined?
So as I said, there can be some like singular points, and these singular points can be singular lines or singular planes depending on the yes dimension that you said. Yes.
Okay.
For example, you can show that when this space is two-dimensional and here n equals 2, then you can show that there must be at least one.
No, when dimensions match, then yes, I agree. Then of course.
But what if the lambda dimension is 10 zillions and you still have only two-dimensional psi? What happens then? Still fine? Everything is technically.
I mean, technically fine. I mean, so there can, as I said, there can be points where the determinant of the metric is 0. That I mean, on the points on this set of points, it's not really a proper metric. So maybe we need to call it something else. But we can still define things.
Yeah, I can understand. You start with considering one state. So this is a abelian version of the theory. Is there any non-abelian version as well? You can start from two degenerate states, for example, the SO2 version.
Yes. So in that case, we need to consider not just one quantum state, but two sets of quantum states. And yes, we can generalize. Yes, to that situation as well. I will not perhaps talk about that generalization, but that's possible.
So has anybody already done that generalization in the literature?
Yes, we could have done it. Yes, thank you. Yes. Okay, yes, hi.
Since the quantum metric is divided in this complex projective space, so it seems the key point to have this definition is you can map your Hamiltonian to this space. So my question is there some condition that this mapping can be there and some condition there cannot be this?
So mapping means
From this
to this
space to this space. Yeah.
So it's always possible. So if you have an n by n permission matrix, then this is a space you automatically get.
So one more related question. If I have a metric tensor in this lambda space, can I push it forward?
Push forward the metric?
Yeah.
I don't think so. Can you?
I mean, at least with when the dimensions match, then probably I can. No?
Can you? I'm okay. If you can define inverse map, then it's of course also possible. But otherwise, I
So
don't.
the way you were saying that there are some singular points,
That's right,
if we take them out of the manifold, then
Yeah. Then, yes. Well, yes, you're right. Yes, you're right. Okay, so yes. Okay, so let me write this. So far I was only looking at one quantum state or one state which depends on the parameter. But let me interpret it in terms of the interband matrix element. So now let's consider some Hamiltonian eigenstate. So now the eigenstate thing. So let me look at the nth eigenstate. And for the fixed lambda, there's a completeness relation that the projector to each eigenstate summed over all the bands or the states is equal to 1. Then using this relation, just the quantum geometric tensor here can be rewritten. So here I have 1 minus the projector to n states, which is equal to the sum over projector to all the other states, like this. And then so this is really the interband matrix element. And in particular, if you look at the diagonal component of the quantum geometric tensor, diagonal component, you can show that. So the diagonal component is symmetric in the indices, of course. So yeah, so it's equal to the quantum metric. And you can rewrite it in this way. So there's a state that you're looking at, take a derivative, and you take an inner product with other states, and then sum over. And that's the quantum metric. So you can write the quantum metric in terms of the interband matrix element of the derivative operator in isolation.
And this is, of course, different for different eigenstates.
That's right. That's right. Yes.
Yeah, in the first slide, you defined psi as a column vector which contained all the eigenstates, psi 1, psi 2, psi 3, up to psi n.
No, why is it?
But there was.
Okay, so that was a confusion. Sorry.
Yeah, in the
basic.
bottom right.
So this is not eigens. Okay, first of all, this is nothing. This is eigenstate. So this is just the first component of this vector, second component of this vector, and the nth component of this vector.
Okay.
So it's not an eigenstate here. It's just state voices.
Okay.
Thank you.
That's.
Okay. Yes. So now let me go to the. Okay, now the definition is done. Now it's half an hour has passed. So I think the definition. Okay. It's nice to have questions, and I'm happy. Yes. Okay, so but what this suggests is that if there is some physical setting where this derivative operator becomes something relevant in physical setting, then if you look at this derivative operator between different bands, and you should get some quantometric contribution here. And then we start from localization. So how it relates to localization. So now I consider the case where the parameter space is a quasi-momentum space. That means I consider a particle moving in a periodic potential like this. So there's a lattice vector. So that's a periodic potential. And then Bloch theorem tells you that the eigenstates can be labeled by a band index n and the quasi-momentum k. And so the eigenvector can be written in terms of this plane wave part times some non-plane wave part, which is also often called the self-periodic part of the Bloch state. And so often in topological insulator physics, what's relevant is the geometric property of this self-periodic part of the Bloch state. I should also mention that if you multiply on both sides the minus ikr, you can see that self-periodic part of the Bloch state is an eigenstate of this quantity, which is often called the K-space Hamiltonian. So we have this K-space Hamiltonian, and we're looking at the geometry of the eigenstates of this K-space Hamiltonian. And the motivation that I want to look at the quasi-momentum space to look for something about the quantum metric is, so this quasi-momentum K is roughly equal to, the derivative of the quasi-momentum is roughly equal to the position, because the derivative of momentum is position. And the derivative operator is something that we should have in order to get the quantum metric. So, and another important relation is if you take a matrix element of this position operator between different Bloch states, then you get this derivative of that matrix element of the derivative operator between two different bands. And this is exactly what we want to get some quantum metric. Okay, and many years before this quantum metric becomes fashionable, so these people knew that quantum metric had something important, and so they look at the one-year function and its localization property. So they're mostly interested in constructing this maximally localized one-year function. And so my one-year function is defined as a Fourier transform of the Bloch state. So there's a Bloch state here, and then Fourier transform, and now I get the one-year function. One-year function, if you use proper phases, is a localized function around here, this point R. So it's a localized object, and then we can discuss how localized it is by looking at the variance of this one-year function. So variance of the position of the one-year function. So x squared minus x expectation squared. Okay, and then doing some algebra. So what I'm doing is I'm writing the second terms in terms of two terms here, and then the final term is obviously positive. So I get rid of this and then use the inequality here, and then do some algebra. the matrix element of the position operator between two different one-year function is using this original definition of one-year function can be written in terms of the derivative operator sandwich between two different Bloch space. So in the end, you get that this quantity is lower bounded by the sum of the quantum metric in phase space over the momentum space. Or you can say it's an integral of the quantum metric in phase space. So localization of one-year function is lower bounded by the integral, momentum integral of the quantum metric.
I think,
Yes.
is there any ambiguity of selection of the center position and with selection of center position? Because this is a space group region. We are stated, we consider the two more large basis atom.
There is no ambiguity there. I mean, so this result doesn't depend on how you choose R.
If zero means the unit cell governed by the unit cell.
Yes, but you know, this is inequality, and there's also there's always some ambiguity in defining in the phase of this Bloch wave function, and that can change this object up here. But the lower bound is independent. The lower bound is the phase gauge independent one. Okay. And so I here I'm looking at the quantum metric in case space, but another natural space to look at is the twist angle space. So when considering disordered system or the quantum many body space, it's natural to consider the space of twist phase in the periodic boundary condition. So I consider some system with a periodic boundary condition, but upon crossing the boundary, or yes, upon going to the other side, I impose some phase twist. So the ordinary periodic boundary condition would not have this phase, but now I assume that there's a twist phase. Adding a phase twist is equivalent also to considering magnetic flux inside the system. So by taking a periodic boundary condition and inserting the magnetic flux, actually minus the phase. And insertion of magnetic flux at the Hamiltonian level can be realized by adding a constant vector potential. So this is a momentum operator plus some vector potential, which will describe the effect of insertion of the magnetic flux in the system. Now my Hamiltonian is written as a function of this inserted phase or the twist phase. And then we can consider the eigenstates of this Hamiltonian, which depends on this twist phase, and look at quantum geometric tensor of the eigenstates of this Hamiltonian, which depends on it. So let me call one eigenstate of this h of theta as psi of theta, and then define the quantum geometric tensor as before. And it has real part and the imaginary part. The imaginary part is often called the many-body Berry curvature. And the real part is a many-body quantum metric.
But now it's not so clear anymore. I mean, you probably still assume that you have some case-based representation.
No, I don't assume.
You don't, right? So then this is now has to be done state by state. In a many-body system, you have zillions of eigenstates in a many-body interacting system.
You're correct.
And this thing there, this many-body quantum metric, will be different for each of them.
That's correct. Right. That's correct.
So how useful is it?
If you do graph state, you have the whole connectivity.
Well, for single, I can go into case space and then things become a bit more simple, maybe if I have just a few bands.
Okay.
Three of them. But here I have zillions and I don't know.
Okay, yes, okay, so what is it useful for? Okay, that's a good question. And okay, let us find out the physical meaning of this quantum metric in this angle space. So as before, I look at the position operator, but now I consider generally a many-body state. So I consider a many-body, or it's a position operator for like all the particles. So A is a particle index, and I sum of it to get the position operator. And
or something. I'm saying.
You can show that the commutator of this position operator and the many-body Hamiltonian is, so in the end, you can write it in terms of the derivative of my many-body Hamiltonian with respect to this inserted flux. So you can write the commutator in terms of the derivative like this. Then, these steps are a bit technical, but considering two eigenstates alpha, so this is a many-body eigenstate. So I take two eigenstates out of this zillions of eigenstates, so alpha and beta, and you act this alpha and beta from left and right side of this commutator. You can show that the matrix element of the position operator between alpha and beta is equal to the derivative of the state with respect to this inserted flux. Okay, what this means is this is a quantum metric defined in the twist angle space for state alpha. So one state, you take one state from these billions of eigenstates. And so here, I can write it in so here I have one minus the projector to this state, and that can be written in terms of projector to all the other states. But this matrix element, so this inner product structure, you have it here. And that can be written in terms of the matrix element of the position operator. So in that, you can show that the quantum metric in the twist angle space is variance of the position operator for this many-body eigenstate. So the quantum metric in the twist angle space tells you how localized these quantum states, the many-body quantum states are. And I mentioned two quantum metrics in different space, one in case space and one in, yes.
In previous slide, like your twisted boundary condition is you are twisting the boundaries only, and then you are defining the metric, and you are saying the localization in the field lattice. How will you understand it? Because you are changing something on the boundary.
Yes, so changing the phase at the boundary is let's say is equivalent to adding a small constant vector potential and adding the vector potential. So if I'm looking at, let's say, the response to adding a vector potential, and it's like adding it's like looking at the response with respect to small electric field.
But in this case, you define, your Hamiltonian is P square. That's why you can do this. But if you have the linear, then you cannot, right? Because in this case, you derivative of H with theta, you have P. And if
So
P has a...
okay, you're looking at the...
Yeah.
You want to consider Dirac Hamiltonian.
If you have the Dirac, then basically this definition will not work.
Okay, so I don't have an answer. Thank you, but that's
Because you have P square, that's why.
Probably we can go to the lattice version and define for the previous space.
well, so for the lattice, I need to consider higher space. Okay, so I look at this case space and the twist angle space quantum metric. Let me explain how they're related. So I think the type I have some severe time constraint now, so let me just go to the conclusion here in the slide. So what I consider is, as a many-body state, I consider a non-interacting fermions filling one band, or maybe partially filling one band. And I consider that specific state, non-interacting fermions. And then for that state, I can show that the twist angle quantum metric is equal to the sum, or say the integral of the K-space quantum metric over occupied state. So they are related. So they're exactly related for non-interacting fermions. So they are looking at a very similar structure, and well, they're both essentially looking at how the system responds to the position of it. So they're related. And yes, let me go then to the third part, how it's related, quantum metrics related to optical response. And by optical response, I mean I consider applying an AC electric field along one direction, let's say X direction. So this is an electric field I want to apply. So it's AC electric field, which depends on time with some frequency omega. the effect of this electric field can be included in the Hamiltonian in terms of the time-dependent vector potential, because the time derivative of the vector potential is the electric. So you can include this electric field by considering this kind of vector potential. But we had a vector potential before. So vector potential, so adding some position-independent vector potential is like adding a twist phase or the flux through the system, which depends on time. So adding this kind of vector potential is equal to adding this kind of flux or the theta that I had in the slide before. And so I'm assuming I'm adding electric field in x direction. So that y and z direction, I'm not adding a electric field. Then the Hamiltonian, including this AC electric field, which can be written in this form. So I have some vector potential term, which is like this. And I expand this Hamiltonian in terms of the the amplitude of the electric field. So there's a zeroth order term without the electric field, and the first order term, which contains the derivative of my Hamiltonian with respect to this inserted flux. And there's a higher order term. And now what I want to do is I start from some eigenstate of the Hamiltonian without the AC field. So I start my initial condition. Initial state is this many-body eigenstate of the Hamiltonian without the electric field, which I call alpha, and then see how the system responds. Okay, so I'm writing the same thing here. So I have a many-body eigenstate, and I have the Hamiltonian, which expanded up to the first order. It's like this. And then, so I add this electric field and see how the system transits. So system, I look at the transition of the system from this state that we're looking at. And the transition probability as a function of time can be calculated using time-dependent perturbation theory. You can find it in any quantum mechanics textbook, or it's also often called the Fermi's golden rule. So the transition probability as a function of time has this form. If you look at Griffith's quantum mechanics book, let me explain. So what I have here is the matrix element of this perturbation part between the initial state alpha and any excited state beta. And I also have this term which conserves energy. So this is a Fermi's golden rule. Now I look at the rate of excitation. So this is excitation at the time t. Rate of excitation I define as this excitation probability divided by time, the rate. And I integrate this over the AC field frequency. And that will get rid of this delta function here. But since there's omega here in the denominator, I get some energy denominator like this. But energy difference times, but this matrix element divided by energy difference can be written in terms of the derivative of a state with respect to the system. So in the end, the integrated excitation rate turns out to be equal to the twist angle space quantum metric times some constant factor. Yes. So in principle, by looking at this, you can extract the quantum metric experimentally.
Yeah, question from your derivations, you don't rely on translation symmetry.
No, that's right.
But here the electric field, what are the restrictions on the amplitude and frequency?
Sorry, can you repeat?
What are the restrictions on the amplitude and frequency?
Okay, yes. So the electric field, or the amplitude of the field should be small enough, so that in the first, so there's to use a Fermi's golden rule with delta function here, there's assumption that you need to wait long enough time, but at the same time, we want this to be the perturbation, so we don't want to wait like too long. And for this to, so for everything to be consistent, you need the electric field to be small enough.
And you need to sum over all the states beta,
That's
all the
right.
possible final states.
Yes, I mean theoretically that's right. Or more experimentally speaking, you need to sum over different frequencies. Yes.
One short question, the equation you used, the last one, the, when you.
This one?
Yes.
Okay.
So with the technical, but when I check whether that is the invariant or not, that I transform the wave function, also the tone, or how do I check whether this quantity is there?
The gauge invariance of this relation.
Yes.
I see.
We apply the unitary transformation to the Hamiltonian and the wave function or
So, okay, so the derivation is written here. So so I have this and I change the phase of alpha, for example. Then I'll add phase to both here. And then so here. So there can be something. So I cannot answer the question right now. I will come back to it.
okay.
Okay, yes. This slide, and then the next slide. So let me also relate this to the conductivity tensor, sorry, the quantum matrix of conductivity tensor. So under the AC field with frequency omega, so you can consider how the system absorbs the energy, absorption power. So absorption power is related to the rate of excitation times the energy quantum that you apply to the system H bar omega. So this is absorption power of the system under the AC field. And then from the previous stage, so this integrated excitation rate was related to the two-standard condition quantum metric. But this rate of excitation can be written in terms of the power absorption divided by H bar omega. And in the power absorption, you can calculate this power absorption. Sorry, you can rewrite this power absorption in terms of this duality field, like this. And this you can write in terms of the real part of the conductivity tensor. So what I'm doing here is this J, the current that you have in the system, is equal to essentially the electric field in the system times the conductivity tensor. And then you do this calculation, and ignoring the high frequency terms, you get that the power is equal to the real part of the conductivity tensor. Now you plug this into here, and then dropping all the coefficients, you can get that the real part of the conductivity tensor divided by omega, integrated over omega, is equal to the fixed boundary quantum metric times the factor. And so I showed it for the particular component x component, but it also holds for any components like x, y, and so on. So this is an important sum rule relating the conductivity tensor, or the real part of it, to the quantum metric of the twist angle space. It was shown by Ozawa Mark in 2047. Yes.
Maybe some strange question, but this kind of relations usually many years ago we obtained using fluctuation, some kind of fluctuation dissipation theorem, for example. So here this also shows that this tensor, quantum geometry tensor, is related to basically to fluctuations inside the system.
So like fluctuation dissipation. The short answer is yes. It's yes. And but maybe we can discuss later. But yes, you're right. It's related. No, but it's related. Well, somehow my equations are missing, but still, morally, what's written here is okay.
You can use the blackboard here, if you want.
Yeah, no, it's okay. So what I want to say here is, so far I was looking at the quantum metric in K space and twist angle space, but you can also look at the quantum metric in any parameter space. So like if you're an experimentalist and you can like experimentally control some part of some parameter in the Hamiltonian, and then you can you can modulate the parameter experimentally and look at the response of the system upon modulation, and that will give you the quantum metric in this parameter space, the parameter that you're modulating. So this kind of integrated excitation rate equal to quantum metric, it also holds for more general parameter space. That's what I wanted to say. Now, okay, so measurements of the quantum metric. So what I'm going to tell you is a very biased story, because I'm mainly going to talk about the measurement that I've been involved in. So I'm Paris, but I had some experimental collaboration. And there's some also measurements of the quantum metric by other groups as well. But as far as I know, the first experiment where the quantum metric was estimated in any system was in ultra gases, ultra quantum gases. So the Klaus Senkstock and Christoph Weidenberg in Hamburg, so they realized the model called the Haldane model, which is a topological non-trivial model with the Chern number. They realized Haldane model in ultra gas experiment, and they shake the system. Shaking corresponds to adding an AC field into the experiment. And then they look at the response, how the system excited, and from there they experimentally estimated the trace of the integral or the average of the quantum metric over the momentum space. It was not really quantitatively correct, but qualitatively it's right. So this axis is some parameter in the Haldane model, which induces the topological phase transition. So here's trivial, topological and trivial. And you can show that when the gap closes, the quantum metric should diverge. And so this blue dot is a quantum metric. But ignore this magenta dot with the green dot. So green dot should diverge at these two boundaries. It's not diverging experimentally, but you can show that it's kind of increasing. So that's let's say quantitatively right behavior for the estimation.
And does it show the lower bound of the chase?
Sorry?
Did they show that is the chase satisfies the lower bound?
Lower bound.
Yeah, because we have the Haldane model, we know the Chern number, and we know that like it has some lower bound for the chase of the metric, right?
The lower bound of what's lower bound?
So you have the Berry curvature, you have the lower bound.
Berry curvature. Yes.
So is this confirmed that?
No, here they're not looking at the lower bound of the. So they're doing it. That's right, yeah, they didn't. Okay, so but that was very, like, let's say, quantitative, but still the first experimental observation. And more detailed measurement of the quantum metric and Berry curvature as a functional momentum was also done in external polarity lattice in this paper. But the method they use is totally different. They use what they did is more like a tomographic method, but still they succeeded in extracting quantum metric and Berry curvature in momentum space. And we can also look at the quantum metric in a general parameter space. So I have a 2 by 2 Hamiltonian, which depends on theta and phi. It's very simple 2 by 2 Hamiltonian. And this is, it's a 2 by 2 Hamiltonian, which you can realize is qubit system. And Jamin Kai in Padua University of Science and Technology realized this kind of Hamiltonian using diamond NV center. And they modulated this theta and phi experimentally and looked at the response. And they experimentally extracted both quantum metric and the Berry curvature by looking at the response. And related measurements also appeared in different systems such as superconducting qubit, multi-terminal cross-section junctions, and so on. So this looking at the response upon modulation is a versatile technique to extract the quantum metric. And so I have almost no time, so I want to mostly skip this slide, but this quantum metric is also related to what is called a quantum Fisher information in the context of quantum metrology. And if you want to experimentally determine the parameter So now you have some state, and then you want to experimentally determine the parameter inside the state. And then the estimation, uncertainty in the estimation of this parameter is lower bounded by the Christian information or the quantum metric. There's essentially the same thing for the pure state, and they experimentally also verify this kind of things.
So what is lambda one precisely here?
So lambda one is it's some parameter in the system. For example, this theta can be lambda one and phi can be lambda two. Then you want to experimentally estimate this parameter, but there's some measurement or the estimation uncertainty. That's related to the Christian. Okay, so this is a summary slide. Yes, this is a summary you can read. And what's important is here. So what I could not cover in this talk. So the quantum metrics, so there are many things known about quantum metric, and I couldn't cover everything. Some important things I could not cover are the relation between supercritic density and the quantum metric. And we are studying this, especially in context of the flat bands. And also relations among topology, fractional quantum Hall effect, and the quantum metric. And there's also a very interesting study in this direction. And also effects of quantum metric on the semi-classical equation of motion, especially in the nonlinear response of the system. And there's a huge experimental progress in solid state systems looking at the effect of quantum metric. But I couldn't cover it. So, okay, so before closing, I need to acknowledge my collaborators. But on the theory side, Nathan Goldman, Bruno Mera, Pai Turma, Grazia Sareno, and Bill Fogno are those I work with on the quantum metric. And on the experimental side, Christoph Weitenberg and Klaus Nextop on the ultra-cold gas experiment, and Jamin Kai was doing the experiment on the NB center. I want to acknowledge. And I want to thank you all for the nice questions and listening to me.
Thank you very much for a wonderful talk. And yes.
So I have some questions. So if you integrate the quantum metric over the Bloch zone, what does that geometrically mean? So physically, it means the Wannier function spreading, but does it have any geometric form?
I don't think so. I mean, yeah, no. The determinant of the quantum metric integrate over have some, or actually square root of the determinant of the quantum metric integrate over the space gives you the volume of the space in terms of this. But just one component integrates, I think there is some good geometrical meaning.
Question regarding the relationship between the on the stable space and distance space. You mentioned that somehow find each band. I was wondering, the quantum metric find that each band have a projector of that particular band or projector of time.
So, okay, so that's a good point. Yes, and that's a really good point, which I skipped explaining, and thank you for the question. So here I'm assuming that the many-body state is made of non-interactive fermions filling one band. So I'm only looking at one band. So I'm not looking at two or more bands. And if I fill two or more bands, then there's some tricky issue about the interband inside the interband matrix domain inside occupied band. So I wanted to skip that part. So this simple relation holds for the situation where you're considering only.
Also for I think that question was also mentioned. I'm not sure. But for the interacting bands, is there inequality between the two stable space?
So interacting is
for the generic case, is there like a no inequality or equality between the two states?
so for interacting system, I don't know. So the case space you want to define for the interacting one or the non-interacting case?
I think I understand.
Oh, okay, okay. Another question?
I have a related question about this, the integration of the trace or determinant of the metric of the period zone. You show that this gives the lower bound of the size of the Wannian orbitals or minimally localized Wannian orbitals. In general, does this lower bound is it saturated in the band or
This lower bound?
yes?
So generally, so it depends on how you, so the question is if you can always.
If you can always
Separate by choosing the right phase or not.
right.
For 1D, I think the answer is yes. I'm not 100% sure, but for 1D, I think it's yes. For 2D or higher, the answer is no.
It's not always.
Not always.
Is there any physical significance when the band actually saturates this bond? Seems kind of special then.
I don't know, but maybe people know, but I cannot answer. I don't know personally.
Another related
But I think that in the last term that you ignore, if you have the one year function that localize on one unit cell, then basically this the next term is zero, right?
Like this term?
Yeah, the term that you ignore to have the lower bound is zero. If the one year is localized on unit cell.
Yes, yes.
So in this case, the lower bound will satisfy if you can define the one year wave function localized in one unit cell.
That's right.
in the second term,
I think you're right.
Yeah, the green box. Yeah. If the overlap of two one year function equal to zero, then this coordinate will be
we haven't had seen that.
the x, but if the weight of the one year function is zero on the
But usually one year function, okay, has some tail. So the question is how this tail behave.
Yes, so a related question, sorry, yeah, so this is, of course, you can also do this for a band with a Chen number, where you don't really have Wannian orbitals.
Yeah.
So in Chen band, this integration of the trace or determinant G, does it also mean something in terms of the length scale of the system?
So for the Chern band, the one year function is not localized, it's not exponentially localized, but okay, so we can still define this and
How is it localized?
sorry?
How is it then localized? Is it local? It must be still localized, right? Is it algebraically localized or what?
I think, well, I never looked at this much.
It's not localized.
Not at all. Even. And there are cases where it's maybe algebraically localized
Or
or?
you can construct the bases when they are sort of exponentially localized, but they are not orthogonal.
But if you orthogonalize, then what?
Then I think there'll be at least a few states that will be localized.
Yes. So let me ask you an impolite question.
That's out.
What is all this useful for?
Oh my God.
Why? Let me be specific.
Why should we spend money on that?
Most of what I've seen, it's basically when you use diagonal parts of the quantum metric. When you relate it to measurable quantities, it's always diagonal terms, right? So what I had expected once you wrote down the matrix is that we're going to tell us that from the matrix element of the metric, you look at geometric properties like curvature and Euler indices or something. But you're not doing that, right? You're just reformulating normal stuff that we know how to compute, let's say last equation there, left-hand side, in a new fancy language. So how does the new fancy language help me to do more than what I can do with pedestrian waves from the start? And anyhow.
I mean, okay, so left-hand side, you know how to calculate, but you don't know how small you can get to, and that's given by this. So this new information.
Sorry, I don't know how.
So the left-hand side you can calculate, yes, but let's say you want to make it maximally localized, but generally, okay, so if you don't know this result, you don't know how localized you can make this variables.
But I can compute the properties of projector without using the terminology of a metric.
Yeah.
I can try at least.
No, but I think that's the key point, is that it's an application of this for other physics. That is the part that we doesn't have time to talk about in the conclusion.
But metric is a geometric thing, right?
Yeah, but
I wanted to have some geometric, that you do something like with the geometry of this, but you haven't shown this to us. So, what about curvature properties and all this? I mean, for example, if you were to tell me that in an interacting system, you can show that
in your parameter space, the metric is curved because of the interaction, then I would say, oh, wow, that's marvelous. That's interesting. But you haven't shown this. So what am I missing? Or is this what you're aiming for in the end?
Okay, so you asked, okay, well, it depends on what you mean by geometrical.
Well, look, when Einstein introduced his geometry, right, and his tensor, he said, we don't need to do Newton. We can explain gravity as a curvature in my space, in my metric, right? That is a step, sort of some new information that is in that metric. If I reformulate this, I have a new understanding of what gravity is. Now you're trying to, if I understand you correctly, reformulate quantum mechanics using a metric. But then what is the new understanding that I'm gaining?
As I said, so this will give you the geometric lower bound to the one-year function. If you don't like it,
I think it is a point that it have application, it has application.
It's material-based. Hamiltonian information is becoming the temporary. It gives the different conductor.
Because it's a lecture, right? So it's not total application yet, but it has important application. It's a last slide, right?
And we can compute all conductivity without using Berry curvature. So, when you can ask that, it's used.
What is the use?
I think Einstein's theory is saying that. Maybe I don't see it in maths actually. Maybe I put it on that.
You solve the.
Okay, you should speak louder. You have to be louder. You have to be louder.
Comment from the.
Speak louder, please.
Sorry, I want to add like actually one thing that's mentioned that
Not superfluidity, only superfluid weight. Yeah, it's not yet superfluidity. So
Well, yes,
it's also,
you
you know, like
some important prediction
Yeah.
is that's some prediction.
If you attend the talk last week, you see.
Sorry, so this is
So in like 2D chart insulators, you always have a single variety in the Bloch. So does that always give a divergence of the quantum?
No, it's no. So to calculate the quantum metric, you just need a locally defined continuous function. So it's not divergent.
But we also mentioned the metric return can be zero.
That's right. That's right.
Is there any physical significance? That may be something that is.
That means that for the two-band model in 2D, there must be points where the Berry curvature should be divergent. That's one thing.
what is the physical significance of that?
What's significant?
You know, what does it mean in terms of, you know, physics? If that there is a point where the Berry curvature vanishes. Okay, so what does it mean? What's the consequence of that? Can we conclude?
Consequence, no numbers.
What?
So there's no anomalous velocity at that point.
No what?
No anomalous velocity at that point.
Oh.
So if I had a wave packet, if I got a hand of God a wave packet in that specific point,
Right.
and only in that specific point,
Then-
I apply an electric field, there's no anomalous velocity.
It has to exist.
Yeah, that's a prediction.
We want to like compute.
Well, if I want to estimate that rho,
Wait, so you want how you can experimentally estimate the quantum metric?
or perhaps in a related question, say, if I have a content, it's like I want to do sizes that are beyond. Other ways of this.
So like experimentally, you can estimate the quantum metric using this optical response. And some people have used it to measure the quantum metric in
Okay, so thank you very much for your